So then now, so far in this course, now you guys know how to design good OTAs, fully differential OTAs, 2-stage. Even if the same thing can extend for 3-stage also, right? So again, if things are all nice and good, I don't have to teach you anything further. But fortunately for you guys, we have a lot more to learn. So it turns out in practice, there are a whole lot of things that work against you in your design. And we look at some of those non-idealities and see what we do to tackle them in practice. So the 3 major non-idealities we might briefly discuss in the rest of the course are the following. First, I'd say that, things are all non-linear. So we all nicely say that it's small signal linear circuit, but in practice things are terribly non-linear. And simplest way to explain what is non-linearity is, we expect 1 times 2 is 2, but in practice 1 times 2 might be 2.01 or 1.99. Linearity is not met, right? And second, truth bomb life will throw at you is noise is present everywhere, starting from small resistors, transistors to classroom environments. Everywhere you have noise. And third, there are no 2 elements which are truly identical. There will always be some kind of mismatch between any 2 supposedly identical elements. So we'll see how to analyze or deal with these non-idealities one by one, and we'll start with mismatch today. And for understanding mismatch, it's a good idea to know how things are made on a CMOS process. So I'll just show that how it's done. For that, I'll rely on PowerPoint slides I made yesterday night, because I think it's better explained using slides. There is nothing to derive here. It's just a piece of information that you need to know. Okay, it's not happening. Okay, so let's start with how things are made on a CMOS process. So let's start with our hero or heroine, the NMOS, PMOS transistors. So how do you think an NMOS transistor is made? Some of you must have taken some courses on device fabrication, semiconductor devices. What is the base on which things are made? You have a p-type semiconductor or p-type substrate. So you have a p substrate like this, on which you put 2 n plus regions. So this one acts like source, other acts like a drain, and this is your gate. Same thing for PMOS transistor. The only difference is you make it inside an n-type semiconductor. So you have a common p-type substrate in which you make an n-type semiconductor. We call it as an n-well, and then you make source and drain and gate here. And usually, not usually, it is the case that all these vertical dimensions you see, right, they are not under your control. It is kind of fixed by the fabrication process. So the only dimensions that are under your control are these 2. And remember, this is the width of the transistor. This is the length of the transistor. Okay. So instead of showing a 3D picture all the time, so we typically look at 2D picture where we show only the dimensions that are under your control. So we look at the top view of this thing so that we look at only width and length. And if you do that, your engineering drawing course, so look at the top view of this, that's how it will be. And this is your width and length. Same thing for PMOS transistor, that's how it will look like. So typically when we do what is called layout is where you actually, it's like a civil engineering thing, like building a building. You physically decide where each element is going to be present on your silicon substrate. And when you do that, this is the view that you will see. A transistor will look like this, an NMOS transistor will look like this, a PMOS transistor will look like this. Of course, the colors are random colors I have used. It won't be this color. Okay, so longer, that's the way I have drawn. I mean, this is length is what that matters. Okay. Now, I mean, if we show it here, what I'm saying is, if you want your transistor to be of particular width, the gate has to follow. I mean, or it might be slightly shorter, I don't know. So all you worry is about these 2 dimensions. Okay, so you only worry about length and width. Okay, so now MOSFETs you know how to make, but we also need to make connections. To make connections, what do you use? Metal lines. And what metal do you think we might use for what element do you think is used for this? Huh? I mean, something that you want to connect 2 points. Yeah, it has to be a metal, but what element do you think is used? Aluminium. Yeah, aluminium is slightly costly. So typically, what is the next cheaper thing? Yeah, that's what is used. So for showing that, I will show a 3D picture. So we'll have multiple copper metals like this at multiple levels, so that you can have different options for connecting. Again, since here I could draw only 3, I have drawn 3. But in modern processes, you can have 8, 9, 10, 12 or anything. Different copper metal layers, everything is available for connection. And sometimes in some modern processes, you might have at the top level, you might have an aluminium metal like you guys mentioned. And that will also be a thicker metal, so that resistance is much smaller. But might not be available in non-processes. So if I show the side view of this, so I'll show the side view so that you can see all the metals clearly. Oops, sorry. This is how it will look like. So here I have shown essentially 4 metals like this. Okay. So now, do you think I can keep these metals floating in thin air like this? So what do you put? Yeah, some kind of dielectric or some kind of insulating material. I don't know what is it. Something will be put. Okay. And let us say now you want to connect this. Let's say I call this to be drain of NMOS transistor, drain of this PMOS transistor. I want to connect these two. But remember that this is a semiconductor. For connecting it, I have to connect using a metal. So we usually have what is called as a contact. Right? And from this contact, you have to connect to this metal and then make this connection. Right? And for that, we have something called as a via. Think of it like a pillar that connects these two. That's it. You don't have to worry so much. So now it's connected this way. Now sometimes you might decide that I don't want to connect it using this metal M1. And let's say I want to connect it using metal M2. So in that case, you have to have one more level of via. So you'll have, this is metal 1 level, this is metal 2 level. So you have one via and another via, and then don't connect it. That's how it's done. And similarly, if you want to go for third metal, you will do this. This is not exactly how it might look like. A very representative picture, what I could quickly draw in PowerPoint yesterday night. Okay. Oops, sorry, what happened? Yeah. So another thing about most CMOS process is this. So as you see, the P substrate is common, and all the NMOS transistors share the same PMOS substrate. Share the same P substrate. So which means P substrate, remember, is your fourth terminal, the bulk body or substrate terminal. That is all common for all NMOS transistors. And usually you don't want this PN junction to be forward biased. So you connect this to be at the lowest potential in your circuit, and that's usually ground. So that's why for all NMOS transistors, typically we connect the bulk to ground. You don't have a provision to connect it to any random potential. But there are specialized processes where you can exercise control on where you can connect your bulk to be. For that, what is done is this. This is your normal NMOS transistor. The idea is you want to isolate this P substrate, the P-type the P-type thing. So you make another P well, but you make sure that first you have an N well and then make another P well. So this way, these two things are isolated. So this you can connect it to anything you want. So this is typically called as a triple well process. Might not be available, like everywhere. And as I already mentioned, all these vertical heights, the thickness of the metals, the distance between the metals, everything is fixed. You don't have control on that. Cool. So now at least you have some idea on how MOSFETs are done. And in addition to MOSFETs, what are the things that you need in your design? All passive resistors, capacitors, inductors are also, but we are not dealing with inductors in this course. So how do you think resistors are made? Sorry? What conductors? Yeah, I mean basically you take any material which has a good resistivity and you can use it as a resistor. So there are multiple variants of resistor. So let's say it is something, maybe high resistive poly or something. Okay. So some material, and let us say dimensions of this piece of material is this. Let us say I am interested in the current flow in this direction. What is the resistance of this slab? Go back to your 6th standard physics, 8th standard physics. Go into L by, yeah, cross sectional area is this cross section WT. So that's what you get. And as I mentioned, this thickness is not under your control, that's a vertical dimension. So again, if I show the top view of this, it will look like a rectangle. So only the width and length are under your control. Okay. So similarly in the resistance expression, I take out rho and T, which are things that are not under your control. Resistivity is fixed, thickness is fixed, and remaining is L by W. And this ratio rho by T, we call it as sheet resistance. And what is the units of this strictly? Ohms. Okay, but in practice we say it's ohms per square. Again, the reason is for convenient reason. Again, the reason is this. See, if I know the sheet resistance of this material, to find the total resistance, all I need to do is count the number of squares in this. That is, for example, let us say the length is say 6 micron, width is say some 2 micrometer. So I know that I have 3 squares here, right? Square 1, square 2, square 3. So my total resistance is sheet resistance times 3, right? So that's why it's called the units, we call it as ohms per square. And a typical number for a sheet resistance can be anywhere between say 80 to 100 ohms, and it can change a lot depending on the process and the material. Just a rough number I'm giving. Okay. So this about resistor, pretty simple. What about capacitors? How are capacitors made? Yeah, the parallel plate capacitor, metal, 2 metals, and then put some dielectric. But remember, in your process right now, we have, let us say, multiple metals like this. Say I have metal 1 to metal 6 here. I can form parallel plate capacitor between any two of these metals. So for example, let us say I can form parallel plate capacitance between the metals in the lowermost levels, or I can form capacitance between the metals at the topmost levels. Which one do you think might be better or not? Do you think one of them is better or both of them are same? I can't do anything.
The lower one would be better because the thickness between them seems to be smaller.
Oh, you're saying this distance, huh? Okay, that's not a problem. We can have a larger area to get the same cap, let us say.
So we'll have smaller area to get the same cap.
Maybe, but one important thing is, see, notice that I have, two parallel metal plates here. There is capacitance formed between these two. But is there some other capacitance getting formed here? I mean, remember that this is a metal, this is a semiconductor. So you will have a parasitic capacitor between these two. Same you will have from the top plate also to this, but that from the top plate to this, that's going to be very small. So anytime you form a capacitor like this, from the bottom plate to the P substrate, you will have a parasitic capacitor. Yeah, even from the top plate you will have, but that is not so much, right? So if this is, and based on this, which is better? Top one, right? Because here it's going to be much smaller. So typically these kind of capacitors, these are called as MIM capacitors, metal insulator metal, and these are made usually at the topmost metals. And sometimes you will find that two special metal layers are reserved for making capacitors alone, and that could be something like this. One metal layer can be just below the topmost metal, one can be just above the topmost metal, and capacitance might be formed between these. Two separate metal layers might be reserved only for capacitors, making capacitors, and not for connections. So usually it's done at the top. Okay. Okay, did you were you convinced with the fact that there is going to be a parasitic capacitance from the bottom plate to this one? This is fine. So now here here also I'll have a parasitic capacitance from the bottom plate of this capacitor to substrate. But which of these two capacitors do you think is larger?
Parasitic of the smaller one will be larger.
Right?
But area of the
No, that's not a problem. No, I mean, see, the way I've drawn it looks like the spacing is a lot, right? But in practice, it might be same. Okay. Like I told, usually you have separate metals for making the capacitors, right? So these can be made with the same distance, right? So a main concern must be the parasitic capacitors. This will affect your design directly. Okay. Okay. Just a brief explanation. So nothing to. Okay, so if I look at the capacitance, now it will look like this in a 3D view. Looks like a nice cake that you can eat, but unfortunately cannot. So here again, if I show the dimensions to be this, what is the capacitance of this structure? Epsilon WL by D. So that's what will happen. And again, this vertical distance is not under your control. Epsilon is not under your control, so you take these two out. So we call this to be unit capacitance or CU. And what is the units of this thing? Farad per meter square. A more practical unit is femtofarad per micrometer square. And I mean, a good number for such MIM capacitors is the unit cap can be a few femtofarads per micrometer square. Maybe 2 femtofarad, 1 femtofarad per micrometer square. Okay, great. So now you know how to make, how MOSFETs are made, resistors are made, capacitors are made. You can put all together to make your, let's say, nice op amp. But in practice, you don't fabricate one particular chip, one particular design. You fabricate an entire silicon wafer like this. Look at a silicon wafer, it will look nice, shining, you know, like material. And typically the diameter can be, a typical diameter is about 300 mm. That's one of the standard sizes. So you make sure you fabricate the entire silicon wafer. So your design is essentially replicated all over the silicon wafer. And finally it is kind of diced like this. So I can show the picture here. So design is replicated throughout this and then it's finally diced like this. Right? So that you can get the individual designs. And finally these are called as dice or chips, whatever you call it. And again, depending on the area of your individual die, you can get several hundred thousands or millions of chips in one wafer. Right? Great. And I can show actually pictures of this. So yeah, this is a real picture of a silicon wafer. And in fact, I found this in this website. And interestingly, this is a website where people sell, bid and auction all collectibles, you know, all this antiques kind of things. And some guy was actually selling this. And this is actually 1980s National Semiconductor CPU, a real silicon wafer on which this was done. And you can clearly see, you know, like individual designs there. I think the number of designs here is smaller and the wafer size might also be small. This was a long time back. And if I zoom in, you can see the individual designs. Cool. So now let's say I have a silicon wafer like this. Let's say look at one particular chip, and let's say in my particular design I have a resistor, and let us say the resistor has a nominal value of 1 kilo ohm. Let's say I have another resistor placed close to this in my design. So what do you think in practice the value of this resistor might be, or what do you expect it to be ideally? 1 kilo ohm. But as I just mentioned, no two elements are identical in practice. This will not be 1 kilo ohm, simply because the fabrication process happening in this location might not be exactly happening here, right? So I mean, a simple way to understand this, see here I have not drawn nice rectangles. In practice, we cannot etch out nice rectangular shapes. You'll have all kinds of weird geometries. So the geometry you see here might not be the same as the geometry here. So the resistance value will be widely different. So let's say in my design I have 1000 such resistors. Why? I don't know, I'm obsessed with resistors. I have 1000 resistors in my design. And finally I get the chip back. I measure the value of all 1000 resistors. And then I try to plot distribution. That is, in x-axis I am plotting the number of resistors. No, x-axis I am plotting the resistance value. Y-axis I am plotting the number of resistors having that value. How will the distribution look like? Gaussian. Again, central limit theorem. Several number of independent, identically distributed random process. They all finally add up to Gaussian. So it will basically look like this, right? And what do you think the mean value of this might be? 1 kilo ohm. Yeah. Mean value is the expected value, and we expect that the value is 1 kilo ohm. Should not be surprising. And this variation in the resistors within a particular chip, we term it as random mismatch. So this is, I will say, intra-die or intra-chip variation. Okay. So now let's say this is the chip, this is the wafer, this is the chip I looked at. So here I saw the mean value of all the resistors, and they are very mean, and they are 1 kilo ohm. Now let us say I look at this chip here, do the same experiment, I find the mean of all the resistors. Here they are not so mean. So here you might find that this might be 1.2 kilo ohm. Similarly, let's say I take some chip here, the mean value here might be 0.8 kilo ohms. Again, reason is simple. The fabrication process happening in this location will not be exactly identical to what happens here to what happens here. Okay. So which means if I take any particular chip in my wafer and find the mean value of the resistors, it will vary a lot. And so let us say this was from one chip, this will be the distribution for another chip. So let's say this was 1K, this might be, oops, I don't want subtitles, how do I do? Okay, fine. $1.2K, and this is 0.8K, this might be say 1.2K. So if you take any chip in the wafer, it might have, one of them might have distribution like this, something like this, and so on. So the process or the foundry is the place where foundry is the entity which fabricates the chip. They will kind of guarantee that if you take any chip in the wafer, the mean value might be within a range. So let's say that range can be 0.8 to 1.2K. That is something they will guarantee. And this variation in this mean value, we call it as process mismatch or process variation. So this is essentially the chip to chip variation. Now in addition, if you take one particular chip, around the mean you will have variation in the resistance value, and that is what we call as random mismatch. This is the terminology that we use. So I have taken an example of a resistor, but even if you take a capacitor, same thing will happen. Capacitance value will also have the same distribution. And even if you take a MOSFET is no exception. You will also have something, but for a MOSFET, the properties you are interested in are, say, the threshold voltage and the mu n COX W by L factor. And both of them also, if you take it, they will also have a Gaussian distribution. Okay. And for the process variation in the MOSFET, we kind of give some special names. So let us say you take some MOSFET. Let's say you have lots of MOSFETs in your design, and let us say after fabrication you find that the threshold voltage and the current factor, they all come up to be the nominal value that you expected it. That is typically referred to as a typical case or a nominal case. Now let us say all these parameters turn out to be such a way that the effective current in your MOSFET is very small. If the current is small, what can you say about the speed of the transistors? Slow. So that's typically called as slow. And similarly, you'll have other end where it say it's fast. Now similarly, I mean this is for NMOS, same you'll have for PMOS. So now we can put all permutation combination, and the things that we look are these: slow, that is slow NMOS, fast slow PMOS. This is typical, or it can say nominal NN. This is fast, and this is typically referred to as skewed corners, wherein one of the PMOS or one of the transistors is slow while the complementary device is fast, or vice versa. Typically the first thing is for NMOS, second thing is for PMOS. When I say SF, slow NMOS, fast PMOS is the convention. And the jargon given to this is process corners. Okay. Yeah, I mean, you can see, typically you want the extreme cases. Okay, I'm not going to details. In I think 619 it might be covered. So you just look at the extreme cases, what all can go wrong. Okay, sorry, yeah. And in addition to this process variation, in practice you will have variations in your voltage. You expect that supply voltage is, let us say, 1 volt to your circuit, but in practice it may change because maybe you are powering it from a battery is discharging, voltages will change. And you will also have variations in your temperature. You cannot say that your design will work only, like in March in Kanpur. If you go to January, it may not work. In July, when it is ultra hot, it will not work at all. It has to work across all temperatures. So temperature is another thing that will work against you. And in practice, these three things are called as PVT variations. And as a designer, your job is to make sure that your design works even in presence of variations in process, voltage and temperature. So just to make sure that things are clear with respect to the process and random mismatch. So the idea is this: if I take one particular chip and look at the value of, say, resistors, for example, the resistance value will have a distribution with some mean, right? Now if I look at this mean value across all multiple chips, this mean value will change. For example, from the nominal value, it can change by plus or minus 10 to 20%. This variation in this mean value is what is called as process variation. That is the variation from chip to chip. Okay. Now in a particular chip, as we saw here, there is going to be variation in the resistance value. Around the mean, there is going to be variation in the resistance value, and this is called as random mismatch. That is, within chip, the variation in the component values, that is what we term as random mismatch. Okay. So now this is essentially what I am plotting is the distribution of the total resistance, that is the mean plus the variation. So now let us say if I want to find the distribution of only delta R, how will it look like? This is the distribution of the mean value plus delta R. If I look at the distribution of only delta R, how will it look like? Same with what value of mean? 0 mean. So we are just subtracting the mean value from it, so it will essentially look like this. Okay. So this is a random quantity. We have to quantify this. What do you use for quantifying random things? Yeah, all these statistical measures, mean, variance things. Mean is 0, no need to worry. So only the variance or the standard deviation we look at. And let us say I look at the standard deviation in the variation. And now let us say just couple of minutes I'll wrap up. So let us say you take some particular process, you fabricate 1000 resistors with a nominal value of 1 kilo ohm. You find that in your particular chip, the standard deviation in the resistance value is 100 ohms. Now let us say I have another resistor with a nominal value of 10 kilo ohm. I fabricate, let us say, similarly thousands of such resistors. So if the resistance nominal value is 10 kilo ohm, what do you expect the variation in the resistance value to be? 1 kilo ohm. I mean, the resistance value is large, the variation will also be large, right? So, but does it mean that, when I do this, my process has become worse? That is, earlier the variation was 100 ohms, but looks like now it's 1 kilo ohm. The question is the process become bad, the fabrication process? The same fabrication process. So, looks like my sigma is varying a lot. So, this is not the right way of quantifying the mismatch. So, what should I do to have a fair comparison? Yeah, basically you have to you just cannot take the absolute value, right? You should normalize it with respect to the nominal value, right? So that's what we do. This is not a bad process. It is the issue with the way we are quantifying the mismatch. So we actually look at what is called relative mismatch. That is, you take sigma delta R divided by the nominal value R. And this actually sigma of delta R by R, this is essentially equal to sigma of, that is, I am taking standard deviation of a random quantity multiplying by a constant. It is same as taking the standard deviation of the quantity scaled by a constant, right? That's all. So this is the quantity that we use for quantifying random mismatch in practice. Okay. So so for resistors and capacitors we do the same thing. For MOSFETs, yeah, and this sigma delta R by R and sigma delta C by C can be actually as low as 0.1%. That is, the random mismatch can be kept very small. But if I look at the process variation, that is the variation in the mean value from chip to chip, that can be as high as 10 to 20%. That is, in a particular chip, you can make sure that the resistors and capacitance values might not vary a lot. By 0.1% only it can vary. But if I look at the mean value of the resistors between chips, that can vary quite a lot by 10 to 20%. So for a MOSFET, for the current factor, we normalize it and look at relative mismatch. For the threshold voltage, we just look at delta VTH. We don't normalize it with respect to VTH, simply because we can have transistors with threshold voltages as close to 0 as possible. So then this will just blow up. So only for threshold voltage, we don't normalize it. And it turns out all of these relative mismatch quantities, they are inversely proportional to square root of area. Again, it's just a I'll give an exercise problem so that you understand it. So which means you can say that this is this, this is this, same with all. So what is the units of this, by the way? Sigma delta R by R? No unit. So what should be the unit of this proportionality constant? Yeah, I mean, but what is the unit? Meter, not meter square, meter, right? So this will also have a units of meter. This will also have units of meter. What is the units of this? Voltage. So this will have units of, yeah, voltmeter. It's not the voltmeter, the meter that measures voltage, but yeah. And this is typically called as Pelgrom's model. Okay. So we'll stop here and we'll continue. So I think Saturday seems to be Friday's timetable. So we'll stick to the same timetable. I'll not have extra classes. No project extension, unfortunately. Those two are independent events.